I want to talk a second about the P-series problem. This is a famous example that makes all the calculus textbooks, and it's based on this series right here. And what we see here is we've got the sum from 1 to infinity of 1 over n raised to the p power. Looks straightforward. The question we're asking here is, what is the impact of the size of p? And what we're going to look at is, if p is less than 1, what happens? If p is greater than 1, what happens? And if p is equal to 1, what happens? We have to separate this out as a special case because we're using the integral test, and you'll see in a minute how this is a special case. We have to derive a different way of coming about the integration. But so, to start with, the first part of this, I'm going to ask these two questions. If p is less than 1 and if p is greater than 1, do we get convergence or divergence based on the integral test? So first thing we got to do, of course, is integrate this. And so I'm going to rewrite this something like this, 1 to infinity. And what I would often do here, you don't have to do it this way, is I think about, well, what is my variable? Well, I'll make that x raised to the p power dx, something like that. And this is what I'm going to integrate. But of course, you know me, I would not integrate it this way. I wouldn't think about it quite that terms. I'd say, just because it makes more sense to me, minus p power. And then when I integrate, I'm going to get something of the nature of 1 over minus p plus 1 x to the minus p plus 1, just following the power rule. And this is going to be evaluated from 1 to infinity. And I probably wouldn't leave it like that because those minus signs sticking out front sort of are offensive to me. So I would write this as 1 over 1 minus p x raised to the 1 minus p power evaluated from 1 to infinity. Now I'm happy with the look of that, and I can now start evaluating this, thinking about, well, what would happen if p is less than 1, and what would happen if p is greater than 1. So I'm going to be right around 1 and saying, well, what if it's a little bigger? What if it's a little smaller? What's going to go on? Okay, so back to our equation, and we can see when we evaluate this, I suppose a slightly better way to say this would be 1 over 1 minus p times the limit, as maybe b goes to infinity, of we've got b 1 minus p minus x. When we plug in the 1 here, we get just 1, something like this. And we can take a look and see what happens now. What is our limits going to be? Well, if p is actually less than 1, come back up here, it's less than 1, what happens here? Well, we get 1 minus a number that's less than 1, so that's a positive number, a positive power. Infinity raised to any positive power is going to be infinity. Okay, so if p is less than 1, we diverge. P is less than 1, diverge. What if p is greater than 1? Well, then we get 1 minus a number that's greater than 1. Well, now, wait a minute. That would be the equivalent of writing it, let's say that 1 minus p is going to be negative, equals some negative number. So that's more like thinking about it now. It's 1 over b raised to some power q, whatever this difference is. That series is going to go to 0 at the limit. And then this simply becomes now 1 over 1 minus p times minus 1, which means that we get convergence to 1 over, we play with our minus signs. This will be what this integration goes to. And that does not tell us what this series converges to. It just tells us that it converges. Okay? So now we get the situation when p is greater than 1, we converge. Okay. Later we talk about error terms and remainders and things like that, and we can see how we can use something like this. But for right now, all we're doing is a test for divergence and convergence. So we've solved here. We know that when it's less than 1, we get divergence. When it's greater than 1, we get convergence. And now the only question is, what happens when p is exactly equal to 1? Okay, so let's go back and do our integration. Here's our original problem, but when p is equal to 1, it really looks like this. It's just 1 over x dx from 1 to infinity. And when we integrate that, we get natural log of x evaluated from 1 to infinity. And since the natural log of 1 is 0, we get that this is going to be equal to something like that, or we could rewrite it, obviously, limit as b goes to infinity of natural log of b, however you want to think about it. And in both cases, obviously, this is going to go to infinity, indicating that this last situation, we get divergence as well. Okay? And in fact, we know this, which is also called, I think, the harmonic series, that's one that we've talked about before, and we know that it diverges anyway. Now, when you go through your book, and I recommend you do, look at example 3. They derive it in slightly a different way, very close to what I've done here, but you should look at it and see how they did theirs and come up with these answers. But you should be aware of this problem. Could show up on a test, kind of a fun, at least it passes for fun in calculus class, example of using the integral test.